as Yugang has mentioned, I have been studying nuclear symmetry energy for almost like 25 years in studying several issues. I have listed my collaborators in China. I work on some of the issues with my collaborators listed here. I learned a lot from them. I want to thank all of them for collaborating with me in solving some of the issues. I also want to mention that Kaskipan, Fu Rong in China has been working very hard in promoting, running this program. It's still active. We still have some money. Hopefully, after the situation getting better, we can continue some of the activities. So thank you for your support to Kaskipan and for collaborating with me on solving some of the issues.
真逗，这谁呀？
Okay, so let me first show you a few slides, which hopefully give you some general information about what is symmetry energy, what's the current situation, and then I'll move on from there. Okay, many of you may have been studying the nuclear phase diagram in the plane of temperature versus density. There are many interesting issues that has been studied for a long time. Now, with observations of neutron stars or reactions with radioactive beams, we have the opportunities to study how everything on this plane may evolve as a function of isospin asymmetry. So we now have some great opportunities to study some new questions along the direction of isospin asymmetry. If you look at the energy per nucleon in asymmetric nuclear matter, we have this isospin asymmetry appearing here. The coefficient of this isospin asymmetry squared is the so-called symmetry energy. It's basically the difference between energy per neutron in pure neutron matter and the symmetric nuclear matter. So this difference is the symmetry energy. For those of you who are familiar, have been studying symmetry energy, you heard a lot about the error parameter, which is used to characterize the slope of symmetry energy around the normal density. Since the symmetric matter has a minimum at saturation density, therefore the error is just proportional to the pressure of pure neutron matter. So error can tell you directly something about the pressure in pure neutron matter. Now, if you write down the pressure as function of density and isospin asymmetry, you can infer from there and write it down analytically the symmetry energy, the density dependent symmetry energy in terms of an integration, which involves the difference in pressure for pure neutron matter and symmetric nuclear matter. So we know that some of the properties of observables in nuclear structures or nuclear reactions are sensitive or reflecting to pressure in asymmetric nuclear matter. So by using observables in nuclear reactions or nuclear structure, we can infer from there the density dependence of symmetry energy. Okay, people have been working very hard in trying to constrain nuclear symmetry energy for over 20 years now. Back in 2013, when we looked at the available data at the time, from the literature, we can see how the expected slope of symmetry energy at a normal density may agree or disagree. And from there, we see that most of the analysis give a slope of symmetry energy around 58.9 plus minus 16 MeV. As time goes, the more analysis. By the time of 2016, there were about 53 analyses available, and this plot shows you the distribution of the slope parameter of symmetry energy. The global average from this 53 analysis gives you about 58.7 plus minus 28 MeV. So as you start to look at the more results from very different analysis, where the average remains roughly the same, but the uncertainty spread out a little bit. So this was the situation, around 2016. Now, during the last few years, since the observation of gravitational waves from neutron star mergers, a lot more information became available.
他以前是我们老师的同学，后来不知道怎么两个人闹掰了，两个人互相竞争。
Okay, now
英国人跑到美国去。
Okay, can you please mute your mic, please? Okay, so this shows you the latest information about what we know about the slope of symmetry energy. We have the earlier systematics from 2013 here, and the analysis from 2016. The recent analysis of neutron star observables give you this green line, which give you the slope of symmetry energy about 58 MeV or so. So basically, this tells you that we have a reasonably good understanding constraint on the slope of the symmetry energy around the normal density. But if you look at the density dependence of symmetry energy from neutron star analysis, this blue line here is the upper limit of symmetry energy from analyzing neutron star observables. This one is the lower limit. You see that if you compare the extracted density-dependent symmetry energy from with the predictions of phenomenological models, you see that many of these models can be ruled out. But here in this high density region, we have a very wide window opening here. This is where we need more information from high ion reactions or neutron star observations. And this is the region where the short-range correlation will play an important role, as we're going to discuss in a few minutes. So on this side, we have some more microscopic of initial model predictions. You see again, this large window, give us opportunity to further study the symmetry energy. Essentially, the available constraint from neutron star analysis cannot rule out any of these predictions from this microscopic many-body series. So we need more direct messengers like neutrinos from neutron stars, or the post-merger gravitational wave signatures. So that's basically where we are about the density dependence of symmetry energy. So at this time, you may be wondering, why is the symmetry energy still so uncertain, especially at high densities? What is the composition of symmetry energy? Where does the symmetry energy come from? And then we can further ask the question, what is the most fundamental but the least known physics underlying the symmetry energy? Okay. Of course, we want to know, what should we do next to further constrain the symmetry energy and its underlying physics. So during my three seminars, I will touch on some of these questions, and of course, you are more than welcome to reach your questions and give us suggestions, and maybe we can establish collaborations to study some of these questions. So during the remaining time of today's talk, I'm going to focus on effects of short-range correlation in nuclei and nuclear matter, and how the short-range correlation may affect the density dependence of symmetry energy, especially at high densities. So what is the short-range correlation? Well, I took a slide from my friend and collaborator, Ali, in Israel. So here in coordinate space, we know that in a typical nucleus at normal density, the average separation between two nucleons is about 1.8 Fermi. But occasionally, some of these some pairs of nucleons may bump into each other, where they will be very close to each other, so close that they will start feeling the repulsive pull of the two of the force between the two nucleons. So short-range correlation, describes the occasional getting together by two nucleons to start feeling the repulsive pull or the short-range tensor force. That's something I'm going to discuss in a few minutes. So in this so-called isospin space, people have found that this short-range correlation is dominated by the so-called isosingulate neutron-proton pairs. Now, if we just look at here from uncertainty principle, when the two nucleons are very close to each other, they have large relative momentum, but a very small center mass momentum. As a result, the two nucleons, after they get together, they will gain higher relative momentum, and they will be kind of kicked out of the normal Fermi sphere. So if you look at the momentum distribution, the momentum distribution of nucleons will form a high momentum tail above the Fermi momentum. Okay. So this is the hopefully give you a general picture about what we mean by short-range correlated nucleons. Now, going back to nuclear symmetry energy, if you look at any nuclear physics textbook, you find a chapter on nuclear binding energy, and you have the mass formula, and you find a symmetry energy term. Okay, here I'm showing you a page from this book. It's one of my most favorite nuclear physics textbook. The reason is because many books just give you a number for the asymmetry energy, say around 25 or MeV, like in Bohr Nielsen's book. This book goes beyond that. It analyzes the contribution or composition of symmetry energy. So you see that here, it tells you that it has a contribution from the kinetic, there's a kinetic contribution. There's 1/3 the Fermi energy coming from the fact that the neutrons and protons have different Fermi surfaces. So this part gives you 1/3 of the Fermi energy. The magnitude is about 12 MeV. Now, if your potential has a momentum dependence, and neutrons and protons have different Fermi surfaces, that potential will contribute to a symmetry energy by this amount here. The last term here is due to the isospin dependence of strong interaction, where this V1 is the two-body kind of volume average two-body interaction in the isotriplet channel, where this we note here is the two-body interaction in the isosingulate channel. the difference here reflects the isospin dependence of strong interaction. And I'm going to talk more about this. But at this point, I also want to tell you that the main message I want you to carry away after this talk is that this term, okay, as I mentioned, normally it's about 12.5 MeV. Okay, I'm going to show you that if you consider Short-range correlation, the first term can become even negative. Normally, it will be reduced from this 12.5 MeV to a smaller number. The exact value is still model dependent, and it can even become negative. Okay, so we need to modify this. If some of you are writing a new textbook, you may want to discuss the issue about the different parts of the symmetry energy. Okay, so let's look at what are the meanings of these different terms, where they are coming from in a relatively simple way. But this slide has a lot of information. Now, if you look at the single nucleon potential in asymmetric matter, let's say the nucleon has a momentum k in nuclear matter with density rho, isospin asymmetry. We have the so-called isoscalar part and the isovector part. This isovector part is repulsive for neutrons, attractive for protons. We have higher order term. This term is an isoscalar term, high order terms. Now, there is a well-known so-called HVH theorem, which relates the chemical potential of Fermi surface, Fermi energy, with the average energy of nucleons. Okay, at the normal density where the pressure is 0, then the average energy for nucleon is just equal to the chemical potential of Fermi energy. Okay, now if you use this theorem and do an expansion on both sides, writing down the Fermi chemical potential in terms of the kinetic part, potential part, do a tidal expansion in terms of isospin asymmetry, and on this side E, the energy, you also do a tidal expansion as the one I saw you on the first slide. Then you can derive an expression of symmetry energy. You have the 1/3 of the Fermi energy plus 1/2 of the symmetry potential plus this contribution due to the momentum dependence of the isoscalar potential. The last term is a relativistic correction. This term contributed only by about 1 to 2 MeV. Okay, this was done by this group in Munich. Now, if you show away the small relativistic correction and introduce the isoscalar nucleon effective mass, which is related to the momentum dependence of the isoscalar potential, then this term can be combined into the kinetic term. Then your symmetry energy becomes 1/3 the Fermi energy of quasi-nucleons with the effective mass m star, okay, plus the explicit direct contribution from the isovector potential U sim1. So this, two terms have very clear physical meanings. If you go ahead to calculate the slope parameter error, okay, at an arbitrary density rho, you have these 5 terms. Okay, you have contributions from, say, the density dependence of Fermi energy itself, the momentum dependence of the isoscalar effective mass, the momentum dependence of the isovector potential. So, it's very complicated. You have at least these 5 terms. Now you think about, if you use different models that may or may not have a momentum dependence in the isovector potential or isoscalar potential, then you can expect to get very different predictions for the slope of symmetry energy. Okay? In particular, if you look at it, the so-called neutron-proton effective mass splitting in neutron-rich matter with isospin asymmetry delta is determined by these 3 terms. The last 2 terms are more or less cancel out. So the effective mass splitting between neutrons and protons is mostly determined by the momentum dependence of the symmetry potential. Okay, this quantity has very important implications for the cooling of proton neutron stars. So it's an important quantity to be studied. So this slide, summarize some microscopic physics behind the symmetry energy. We would like to know more about each term and how to calculate that. Okay, so I mentioned that the isovector potential is a key quantity. Then if you go back to the textbook by these two authors, the symmetry potential can be written as the integration, the volume integration of the isotriplet interaction multiplied by the isotriplet correlation function minus the one in the iso-singlet channel. So you see here, the symmetry potential, the so-called isovector potential, is a direct reflection of the isospin dependence of the strong interaction and the corresponding correlation. Okay. Now, if you look at it, the interaction between two nucleons in the isotriplet channel, we have the same strength for NN, PP, and NP interaction due to the charge independence in the isotriplet channel. But the NP interaction is in this isotriplet channel may or may not be the same as the NP interaction in the iso-singlet channel. By studying properties like Neutron, we know that there is an appreciable tensor force contribution that allowed you to explain the electrical quadrupole deformation of Neutron. So in the iso-singlet channel, you may have additional tensor force, but in the isotriplet channel, the tensor force contribution is known to be very small. So from here, we know that the isovector potential depends on the isospin dependence of strong interaction, and that's something not very well known at the moment. I mentioned that the tensor force may be important in the iso-singlet channel. The tensor force comes in through pion exchange for the long-range part. So at a large distance, the interaction due to the pion exchange give you attractive tensor contribution. While at short distance, the tensor force is mainly due to the rho exchange. That rho contributes a repulsive force. So if you add the pion contribution and the rho contribution, you get this right curve here. Now, as Osuka and his collaborators have discussed in their papers on tensor force effect on energy level splitting in nuclei, at short distance, like below 1 Fermi, people normally use different cutoff or use different forms for the short range tensor force. Okay, this is where the short range correlation become important, and tensor force is the one that does not conserve total angular momentum. It causes the mixing between S wave and D wave. But at the same distance, around 1 Fermi, you also have the repulsive curve. So this repulsive curve can also contribute to the short range correlation. And I'm going to show you a couple of slides illustrating the different effects of repulsive curve and this tensor force cause the short range correlation. Okay, now at the mean field level, if you have a spin saturated system, the tensor force doesn't contribute to the symmetry energy. But people have known, at least since the earlier work by Thomas Cole and Jerry Brown, the tensor force has a strong second order contribution. Okay, so this direct and close terms. If you just use plane waves for the two nucleons, you can evaluate the tensor force contribution through this second order diagram to the potential part of the symmetry energy. As I have shown you, at shorter distance, around and below 1 Fermi, different models use different cutoff or use different forms for the strength of the tensor force. If you use that simple formula, you can translate it directly. This is uncertain short-range behavior of tensor force to the uncertain high-density behavior of the potential part of the symmetry energy. So this will tell you directly, at least in this relatively simple model, how the tensor force will affect the high-density behavior of symmetry energy. Now that's the contribution of tensor force or short-range correlation through the potential part. There is also an effect through the kinetic part. Hans Bethe discussed this in detail in his annual review of nuclear particle science in 1971. He was using this picture. Let's say you have a Fermi sphere here. If you have two nucleons at position B and C, they are interacting through the ice wave. If you turn on the tensor force will cause the mixing between ice wave and D wave. As a result, the two nucleons will populate, will get moved out of the Fermi sphere. As a result, they will populate this high momentum tail above the Fermi momentum. Okay. Now, experimentally, people have been studying the short-range correlation by using electron scattering and proton scattering. From the data analysis, people found that the major contribution to the short-range correlation is due to the neutron-proton correlations. So if you look at the ratio of proton-proton over neutron-proton correlations, this ratio is only about 3%. Okay? So it's really neutron-proton dominated, and that's mainly through the tensor force. I mentioned that at short distance, around 1 Fermi, you start seeing the repulsive curve. That repulsive curve can also cause a high momentum tail. And this has been illustrated, studied in detail in many papers since Migdal. People actually derived an analytical expression for this high momentum tail. The expression here looks complicated, but if you take some approximation looking at it, really far above the Fermi surface, this high momentum tail goes like a 1 over k to the 4th power. Okay, and total fraction of particles populating the high momentum tail here is related to the scattering length of two particles, two fermions in the system. But anyhow, this is a picture at the 0 temperature. What's showing you is here, if you consider interactions among fermions, the momentum distribution is not a step function. Inside, you have a depletion here, okay, depletion of the Fermi C here, and then you have a population above the Fermi surface. So, but this slide showed you that the ratio of proton-proton correlation over neutron-proton correlation is only about 3%. It means that this repulsive curve caused high momentum tail is very small compared to the one caused by the tensor force. Now, the pictures I have shown you, kind of simple-minded phenomenological models, with some of them are done in perturbation series. People have actually studied in great details the momentum distribution of nucleons in nuclei using microscopic many-body series, such as variational Monte Carlo. So here you see the proton momentum distribution from deuteron to carbon-12. Okay, if you look at it, the carbon-12, for instance, the high momentum tail here, calculated numerically, is about 21%. Okay, so that's the strength of the high momentum tail. If you compare the momentum distribution of nucleons in finite nuclei and the nuclear matter, the high momentum tail part remains more or less the same and independent of nuclei, because this is the short-range correlation. That short-range correlation, exists in all the nuclei and the nuclear matter. Doesn't matter, how big the system is, because that short-range part is common. Okay, so this gives you this, universal high momentum tail. There's one interesting question some people have asked: are these high momentum nucleons on cell or off cell? Now, based on my understanding and talking to Joey and his collaborators, these high momentum nucleons here, they are on the mass cell, defined by this dispersion relationship between energy and momentum. So once you introduce dispersion relationship, you have already put the particles on the mass cell. So there are also studies in transport series about the nature of this high momentum tail. Based on the study by the Giessen group, this high momentum tail is mostly coming from phase space effects inside of off-cell propagation of nucleons. So this high momentum nucleons are on the mass cell. Now, we are talking about the symmetry energy and effects of short-range correlation on symmetry energy. So what are the potential effects of short-range correlation on the symmetry energy? Now, I have shown you this illustration by Ali. When you have asymmetric system, like a neutron-rich nuclei, you have a lot of more neutrons than protons. But this short-range correlation is caused by neutron-proton pair. You have to pick up one neutron and one proton, one neutron to make a pair. After they scattered, they interact, they move together to the high momentum tail and form this high momentum tail with a shape like 1 or k to the 4th power. So in asymmetric matter, the minority, the protons, will have more chance to to find a partner to be scattered above the Fermi surface. So as a result, there is a higher fraction. This is a high momentum fraction of nucleons, high fraction for protons to be in the high momentum tail. Okay. As a result, the average kinetic energy of protons are higher than the average kinetic energy of neutrons in neutron-rich nuclei. This is just kind of opposite to what we normally think about in terms of a cell model, where you fill nuclear cells all the way to the Fermi surface, and your neutrons will occupy a higher Fermi surface than protons. But this short-range correlation, just turn over this picture, okay, give you an average, higher average kinetic energy for protons than neutrons. So you can imagine this will affect the symmetry energy. Now, this finding from studying short-range correlation by using electron scattering at a different light and proton scattering at Brookhaven a long time ago has also been seen in proton scattering on calcium isotopes. People at St. Louis did a dispersive optical model analysis, and they inferred the proton occupation, okay, in these 3 nuclei. Okay, so if you look at it for calcium 40, okay, this is above the Fermi surface, okay, compared to calcium 48. In calcium 48, you have more protons occupying the high momentum tail. They also did a prediction for calcium 60. You see more protons occupying the high momentum tail. So indeed, in asymmetric matter, protons are being boosted more to the high momentum tail. They will gain a higher kinetic energy, okay, compared to neutrons. So based on that picture, a few years ago, Bao-An and Li Bao-An and I, we look at how this may affect what's going on in neutron skin. Okay, the study of neutron skin has been a hot topic. For instance, for light 208, you have the neutron density profile, proton density profile. Neutrons are more extended. There is a finite neutron skin, like a 0.16 Fermi. Correspondingly, if you use just the extended Thomas Fermi gas model, we can see that there is a proton skin in momentum space. Namely, protons in the Fermi in the neutron skin will move much faster than neutrons. Okay, and we can give a quantitative measure of how big this proton skin is. Okay, so there's this correspondence between a neutron skin in coordinate space and a proton skin in momentum space. Hopefully, by studying combination of these two, we can learn more about the internal interaction of nucleons inside asymmetric nuclei. So now let's look at in more detail how the short-range correlation may affect the symmetry energy. I have shown you on my first slide. The symmetry energy is basically the energy difference between the energy per nucleon in pure neutron matter and symmetric nuclear matter. Remember, I discussed that the contribution to the formation of high momentum tail due to the repulsive curve is very small compared to the one due to short-range correlation. So if you think about impure neutron matter where you only have neutrons, they may have a repulsive curve. Let's say we put 2% neutrons in this high momentum tail. But in symmetric matter, where you have a lot neutron-proton pairs, where there is a strong short-range correlation due to the tensor force, you have a large high momentum tail. Okay. Now, Xu Chang has demonstrated using this simple formula, but this simple formula has very direct physical meaning, because when you calculate the average kinetic energy, you have to weight your kinetic energy with the phase space. The phase space goes to like k squared. So if you have very small high momentum tail, multiply by k squared, okay, that gives you a big enhancement, to the kinetic energy. So as a result, if you put more than 15% of nucleons in the high momentum tail of symmetric matter, your kinetic symmetry energy, what's plotted here is kinetic symmetry energy as a function of density will become negative. Okay. Now we try to get this paper published. Several referees don't believe the kinetic symmetry energy can become negative, so they rejected our paper. We put it in a conference proceeding, but this proceeding paper has been cited more than 45 times so far. But most importantly is that this simple picture, intuitive picture based on very simple model, okay, has been verified by advanced microscopic many-body series, as I'm going to show you. Okay, so the referees suggest us to do the calculation using microscopic many-body series, which we don't have. Okay, and take time to learn. And but fortunately, there are many experts in the world. They do have advanced microscopic many-body series. For instance, this group in Spain has calculated the different contribution to the symmetry energy using the Bruckner-Hardy-Fock approach. If you look at the kinetic symmetry energy as a function of density from Fermi's gas, without considering the short-range correlation. You have this blue dashed line. When you consider the short-range correlation caused by the tensor force, you have a big reduction. Okay, at normal density, this kinetic symmetry energy is about 0. That's basically what Xu Chang and I had predicted using the simple picture. And this has also been verified by using other microscopic many-body series. Now, if you look at in detail, for instance, using the self-consistent Green's function approach, the kinetic symmetry energy of free Fermi gas is like this yellow one, and this red one is the one considering the short-range correlation. In this calculation, the results depend on the interaction you use, as we can understand, right? The kinetic symmetry energy goes like gets significantly reduced compared to the 12.3 MeV that we normally use as written in many of the textbooks. Okay, in the Bruckner-Hardy-Fock, as I mentioned, the kinetic symmetry energy and normal density is about -1 MeV. Okay, of course, the total symmetry energy remains the same. Basically, you are just shifting the kinetic symmetry energy to the potential part, and the total symmetry energy is about 34 MeV. The slope error is about 66 MeV. Both of them are consistent with the normal value, the so-called fiduciary value we use for many analysis. Okay, we can. Okay, so this is another. Just summarize the kinetic symmetry energy from different microscopic many-body series. They all predict the kinetic symmetry energy are lower than the free Fermi gas prediction. We also collaborated with several experimentalists working on short-range correlation. We extracted the kinetic symmetry energy using the neutron-proton dominance model from their data. And we get this number that are even lower. They are all negative. Okay, like negative 10 or 15 MeV or so. Okay, so this is a big effect. Again, I want to emphasize that the predictions for microscopic many-body series are still model dependent, and the simple model we use in extracting symmetry energy also has drawbacks. Well, now at this time you may wonder, what could be potential effects of short-range correlation on nuclear reactions? This is an important question. Several of us have tried to do it in our transport models, but there are many challenges. We don't know how to do it exactly right. Okay, we have looked at several aspects. For instance, Xu Jun tried to incorporate the spin degree of freedom explicitly, so we can study spin transport and study the spin angular momentum coupling and the tensor force. In order to study effects of short-range correlation caused by tensor force, we have to incorporate the spin degree of freedom explicitly. But we run into a lot of trouble because we don't have enough information about the iso spin dependence of elementary nucleon cross sections. Okay, those are necessary inputs. We also tried to look at the short-range correlation effects on particle production, like hard photon production, through first chance nucleon collisions. Those collisions are sensitive to the initial momentum distribution of nucleons in the colliding nuclei. We get some interesting information, but there are many uncertainties involved in this work. So we need to do more to study how the short-range correlation may affect high-ion reactions. Now, let me spend a few minutes on effects of short-range correlation on properties of neutron stars. Again, this is just some attempts, and there are some issues, inconsistencies about what we do. Like in the relative mean field model, for instance, or in any energy density functional approach. Normally, people write down the energy density has a kinetic term, has a several potential term due to two-body, three-body interaction and so on. Okay, the kinetic term is always written as if you have a sharp Fermi sphere. That's a Fermi distribution for nucleons. But I have shown you, if you consider the short-range correlation, the nuclear momentum distribution in nuclei and nuclear matter are not step functions, very high momentum tail. And that momentum tail is also different for neutrons and protons. If you incorporate this high momentum tail in the energy density function in terms of the relative mean field model, namely you replace the step function everywhere with an integration over the high momentum tail, then your density dependence of symmetry energy will be modified if you require the symmetry energy, everything at the normal density remains the same. Okay, so there's a point, just at saturation point, you have to reproduce the saturation properties and non-empirical properties of some nuclei. If you keep that point the same, then you see that the short-range correlation will reduce the symmetry energy at both high density and low density. Okay, if you look at the pressure in symmetric nuclear matter in comparison with flow data, without considering short-range correlation, you have the blue curve here. With short-range correlation, the pressure increase because you put some nucleons above the Fermi surface. Okay, the particle become more energetic. It increases the pressure. Okay, this increased pressure will allow you to support more massive neutron star and also make the radii a little larger. Okay, so these are some of the direct effects of the short-range correlation on properties of neutron stars within this relative mean field model by considering approximately the short-range correlation effect through the momentum distribution. This approach has been adopted by several other groups. Here I have two examples. The first example is coming from the Brazilian group. They have studied the effects of short-range correlation on global properties of neutron stars and the cooling of proto-neutron stars. For instance, if you look at the maximum mass, okay, with short-range correlation, this is the one with short-range correlation, without short-range correlation, as a function of the incompressibility of symmetric nuclear matter, you have an appreciable significant increase in the maximum mass of neutron stars that you can support. And this difference here, from 1.96 to 2.04 or so are significant. Okay, at the low density, where let's say the transition density from the cross the curve, okay, this is a place this transition density is sensitive to the symmetry energy below the saturation density. So you see this significant effect on the transition density. As a result, this will also affect the tidal polarizability of neutron stars. Similar conclusions have been made by Lu Hao and Zhong Zhou and Baidong in Nanjing. Okay, they considered effects of different shapes of the high momentum tail. Decrease with k to the -3, -4, and so on. In comparison with calculation without considering short-range correlation. So you see that generally the short-range correlation will allow you to support more massive neutron stars, have a little effect on the radii, okay, due to different shapes of the high momentum tail. Okay, during the last few minutes, I want to show you a few things related to the ongoing and planned short-range correlation experiments at different lab. I did electron-ion collider. I did the future, at Brookhaven under construction, and also some experiments planned at GSI and NICA. Okay. Now, one very interesting connection between soldering correlation with the so-called EMC effect. The EMC effect is the one reflecting how the momentum distribution of quarks in nucleons, when nucleons are in the medium, the momentum distribution of quarks in that nucleon, okay, will be modified compared to the quark distribution in free nucleon. Okay, is a medium effect on the quark distribution in nucleons that's moving inside a medium. Okay, this was discovered about 35 years ago. Okay, but the dynamical region for this modification of quark momentum distribution in nucleons that are residing in nuclei or nuclear matter are not completely there's no consensus. One model says that the quark distribution in all the nucleons in nuclei are modified compared to quark distributions in free nuclei. Okay, that's one picture. But analysis by Larry Winston and his collaborator, they found that the strength of soldering the strength of the EMC effect is proportional to the strength of soldering correlation. Okay, this indicates that the quark distribution in all nucleons are modified, but only the quark distribution in the shorter range correlated nucleons are modified. Namely, when nucleons are moving inside a nucleus, okay, normally the quark distribution in those nucleons are the same as in free space, in nucleon in free space. But when two nucleons come together through the soldering correlation, the quark distributions in those two close by nucleons get modified. Okay, that's what this picture tells you. So this is tells us that the EMC is related to the high momentum nucleons in nuclei. Okay? They have recently studied kind of simultaneously the strength of EMC effect and strength of soldering correlation. In this case, in this case, this does look at all nucleons without the scaling. But here in this new analysis, they scaled the strength soldering correlation by the neutron number and the proton number. So this is the strength of neutron scaled, the strength of soldering correlation scaled by the neutron number, by the proton number. You see that for neutrons, as you go from light nuclei to heavy nuclei, the strength of both the soldering correlation and the EMC saturate. Okay, they stopped below before reaching this tidal region. Okay, so there's a saturation when you go from light nuclei to heavy nuclei. But if you look at it, the strength of soldering correlation scaled by protons, it keeps increasing when you go from light nuclei to heavy nuclei. This picture, is again due to the fact that in asymmetric nuclei, in neutron-rich nuclei, protons can easily find a partner to form a pair to fill the soldering correlation of the tensor force. Okay, as a result, the quark momentum distribution get modified, and the momentum of those protons will get boosted. Okay, so this tells us that due to neutron-Bohr soldering correlation, protons in neutron-rich nuclei move faster than neutrons, because in protons you have two up quarks and one down quarks that's orbit to protons. So this from here they inferred that maybe the up quarks are moving faster than down quarks. Okay, in nuclei. Okay, this may have effects on deep inelastic scattering induced by neutrino and antineutrinos, because neutrino and antineutrinos, they scatter differently on up and down quarks. So this has some implications about the neutrino physics. Okay. So there are several ongoing and planned experiments. For instance, people are continuing doing experiments at the different lab using electron scattering on different nuclei to study EMC and soldering correlation. About a year ago, we had a workshop. Many new proposals were discussed. There is also going to be an experiment at GSI. There's inverse kinematics experiments looking at the momentum distribution using peak-out reaction, momentum distribution in carbon-16 and carbon-12. In the future, electron-ion collider, people want to use using collider experiments where you have a large energy momentum transfer. You can probe deeper short-rangely correlated nucleon pairs. When a pair of correlating nucleons absorb a high energy photon, they get a breakup. If they are short-rangely correlated, one will go forward, the other one will go backward. So one design of the detector is the so-called far-forward detector system to measure the recoil nucleons. If we are interested in the physics and the technical design of their detectors, you can read some of their recent papers. So let me come to my summary. To my understanding, the most fundamental but the least known physics underlying the high-density symmetry energy is the spin-isospin dependence of nuclear interaction at a short distance. More specifically, is due to the fact that the neutron-proton interaction in the iso-triplet channel and iso-singular channel are different. There is a strong tensor contribution in the iso-singular channel. The short-range repulsive curve also contribute to some extent, but they have a relatively smaller contribution. But we do need to know exactly in detail how the tensor force and short-range repulsive curve will each play in contributing to this high-density symmetry energy. On one side, we have seen that the tensor force will affect the potential part of symmetry energy, in particular at high densities. It also affects the momentum distributions of neutrons and the protons. They form a high momentum tail, and that high momentum tail is different for neutrons and protons and strongly depends on the isospin asymmetry of the nuclei or nuclear matter. And we have also seen that protons move faster than neutrons in neutron-rich matter. This leads to a reduction of the kinetic symmetry energy compared to the free Fermi gas model prefix. The kinetic symmetry energy is not 12.3 MeV as written in many of the textbooks. It could be very small, can even become negative. So this is what we have learned in terms of the nuclear degree of freedom. We want to use the structure of nuclei, collisions of nuclei and neutron stars to learn more about the short-range correlation and the responsible tensor force and short-range repulsive curve. In parallel to this, we have seen that people have found that the dynamical origin of the EMC effect is probably due to the short-rangely correlated neutron-proton pairs. Only in this short-rangely correlated neutron-proton pairs, the quark momentum distribution get modified compared to the quark momentum distributions in free nuclei. They also inferred that the quarks in protons of neutron-rich nuclei are modified more, and the up quarks may be moving faster than the down quarks in neutron-rich nuclei. as we have, we can see in many of the proposals in the literature, one of the frontiers of QCD is to study the flavor and spin dependence of momentum distributions of quarks and nuclei and gluons in nuclei and the nuclear matter. Okay. Now here I show two-sided arrow with big question marks because I'm interested in knowing the connection between these two parallel pictures. In particular, when we think about in neutron stars, where nucleons are so close to each other, okay, where many people have predicted you must have a quark degree of freedom forming, having a phase transition. But I personally don't know how to make a connection between these two parallel pictures. How do I connect these two degrees of freedom? And I really appreciate suggestions from some of you. Well, thank you very much for your attention.
谢谢保安的非常精彩的报告啊！保安这个报告里面，特别今天给我们讲这个短程关联，在这个物理，包括最后一场报告里面讲到科技物理相关的一些可能的发展。那么大家现在可以这个举手发言啊！我看看叶老师，请您发言。
哎，你好，谢谢李老师的精彩报告。也就在这一页，就是说这个问题也是困扰我，就是我是很关心的一个问题，包括我们设计一些新的实验场是研究这两个自由度的一个关联。然后我就是说其中有一个问题就是您刚才在讲这个 tensor force， 就是在这个有一个 repulsive core， 就是在它的两个核子之间的距离小于1个 femtometer 的时候，我看到您里面说，在这个小于1个 femtometer 的时候，它的 maximum exchange 还是就是它还是可以用 maximum exchange， 就是一个 omega 一个 exchange， 这是我一直很难在我的脑海里面去想象。就是说我们知道就是在传统核物理里面，如果它们距离比较长的话，我们可以用交换这个 meson 的一个图像来解释它们的强作用，两个核子之间强作用。但是在形成短程关联的时候，它们的距离已经是小于一个质子的半径，就是说它们已经是部分重合了。当我一个质子和一个中子已经部分重合的情况下，它们如何用交换 meson 的一个图像来去解释它的相互作用？
OK， 我不是 expert。但是按我 understand 的这个马哈莱的这个 picture， 因为他做这个就一直做这方面的工作嘛。你看这个就是这个 short range repulsion 是 due to rho omega exchange，OK， 这个 short range repulsion， 这个 short repulsive core，OK， 这个 short range repulsive core 它是 conserve angular momentum， 在同时呢，你这个就是有这个 tensor force 这个长程的时候。长程的 tensor force due to pion exchange，OK， 短程的这个 tensor force due to rho exchange， 这是你看这个 positive sign here for rho exchange，for 这个 pion exchange 的这个 tensor force 是 negative，OK， 那你把这个加起来以后呢，就 total tensor force 是这个红线，在这个就 around and below 1 Fermi， 这个 tensor force contribution 和这个 repulsive core 都 contribute。所以这个你有 rho omega exchange， 也有 pion exchange 的contribution， 主要是这个 rho这个omega exchange。
但是说我能理解，在传统的核物理，就是说在夸克模型还没有被建立之前，我们可以用一些这种 meson exchange。去解释，就我们去写一个量体的作用力，然后用一个 meson exchange 的这个图像，就把不同的这个 term 写出来。但是当两个核子之间已经靠得非常近，甚至已经是贴在一起，甚至是已经进入对方的时候，这个时候它已经就是说从我的图像上来说，我已经 无法理解为什么这个时候一个交换一个 meson 这个图像还能成立，或者说我们现在是用一个就依照于传统的一个物理图像去强制去解释一个非常极端的，就是两个夸克两个质子已经结合了。
你说的是对，你说的对，我用了一个 picture， 就是这个 picture 就是完全是在这个海床这个 picture， 但有很多人做，比如像国内梁，他们也还有这个就是国外很多人做这种Meitern quark coupling model， 像Tony Thomas， 他一直就是说考虑这个 nucleon 里边的 quark degree of freedom，explicitly consider quark degree of freedom。OK， 可以从这 quark 这个 interaction 的角度呢去讨论这个 nuclear force。有人去做，我这个 picture 确实这是完全是 stay within 的海床的一个 picture。你可以考虑这个在这个这么 short range 的时候，已经是 inside 的这个 radius of proton。我去年听过你的报告。
谢谢。对，我们要设计一个新的实验，就是用极大的对称的两个原子核，一个是氚，一个是氦三，然后去直接测量短程关联跟 EMC 的这个关联，以及到底是真正是 U 夸克还是 D 夸克，它们的这个 EMC 效果是大于彼此的，就是希望能直接去观测它，因为就是我一直有一个疑问，就是像这种传统的核物理之间的量体作用力，到底在哪一个极限下它已经是作用力了
？OK， 就是这个就是你看那个奥苏卡他们 cut off 在比如说这个 1 Fermi 或者是更就是可能更早。OK， 这下边大家就传统核物理也有人知道这个东西可能不能用，但我们现在是就是有一些人像我们做这个 Neutron-star 的，就是说如果你 stay within 海床那个 picture 的话，就现在就是知道这有问题，但是还是硬着头皮去用它。
好，
这有一点这个样。你的实验是在哪里做？
在 JLab 号 B 已经批准了。对。
OK，great。
好，那个李老师您好，谢谢你很全面和具体的这个报告。然后因为我不是这个领域的，有很多地方我也没听太懂，就是是不是这个 Symmetry 它是决定了，比如说造成了我们这个中子皮，就是相当于是 coordinate space 的一个，而这个 SRC 造成了一个就是 momentum 的一个 tail。momentum space 的一个这样的一个 tail， 然后他们两个是怎么样 interplay 的？然后我没有太懂，能不能帮我科普一下
？OK， 这个就相当于我们受到这个就是做 SRC 的 effect， 他们就发现说这个在 Neutron-rich matter 里边 ，proton 会比 neutron 跑得快。OK。那我们就想说，你在 neutron skin 的 region，OK， 因为这个是在一个 finite nuclei，neutron skin region 是最 neutron-rich 嘛 by definition，OK， 在那个 region 里边，你也有一些 proton， 那些 proton 呢，就说due to short range correlation， 会比这个 neutron 要跑得快 ，proton 要比 neutron 跑得快，所以我们就用一个就是简单的就是 extended Thomas Fermi model。把这个 idea 把它 quantize， 就是把它quality 就是想看 quantitatively how big is the proton skin。So corresponding to 这个 proton skin， 这是你 proton 就是在说里边这个 proton 的这个 momentum average average energy，proton average energy 和 neutron 的 average energy。就在这个 high moment 就是在这个 neutron skin 这个区域里边，这个 proton 的 average kinetic energy 比 neutron 要高，确实高。再从另一个讲，就是我就说这个 picture 也和我们说的这个刘维定理的那个 picture 也是一样的，对吧？就像你在 phase space 里边，你那个 fluid 的那个 phase space 里边， 那个density 是就相当于是 conserved。那这个还没有。
他们两个interplay 是指你是指互相影响吗？他们两者？
对，这个是就相当于是互相影响。我们要算这个 proton skin 的是要用这个 neutron skin 的这个 data， 将来。这两个是 corresponding。
那个就是 Symmetry 它的强度用那个字母大 L 那个斜率表示，这个SRC 的强度用那个 A2 表示，是吗？
对，
他们的就是我用一个 number 去表征它谁强，它的强度的话，那个 A2 是指什么意思
？OK， 那个 A2 它是那样，它就是用来 measure 这个 strength of solenoid correlation。就实验上它是测那个 electron 的那个 inclusive cross section， electron on light 208， 它测这个就是 inclusive cross section as a function of the momentum transfer 是 momentum fraction。OK， 然后呢用这个丢窗做 base， 你测的 electron inclusive cross section on light 208 over inclusive cross section on 丢窗，这个 ratio 会稍有一个 plateau， 在这个就是 1.5 倍的 Fermi momentum 那个 region 有一个 plateau， 那个 plateau 呢，大家就是按照 Frankfurt 他们的theoretical analysis 是 due to 这个 solenoid correlation。第一个 plateau 是 due to two body solenoid correlation， 在更高的 momentum 的地方有 second plateau， 那 second plateau 呢 due to 这个 three body 的correlation。那 three body correlation 现在还没有完全确定下来，在第一个 plateau 就是定下来，那个 A2 的话就是相当于反映这个 ratio of inclusive electron scattering on nuclei on hyphen nuclei over neutron， 那个 ratio 能反映这个 strength of solenoid correlation。
这个 A2 是实验上可测量的这样一个。
对，实验上测量的。
对，这个 A2 它就是这个 inclusive cross section， 它背后对应的是它核子的 momentum distribution， 就是说它有一个在一定的模型下面是有一个一对应的。所以当我们把比如说我一个 carbon 的 inclusive cross section 跟 deuterium 的 inclusive cross section， 然后在 x 大于 1.5 的时候，就是说通过模型我们认为 x 大于 1.5 的时候，它这个 Fermi momentum 是远大于它的 momentum 是远大于 Fermi momentum， 大概是在400个 MeV 左右，就是我们认为这个时候已经是短程关联了。所以他研究的就是说我在 carbon 里面我形成一个短程关联的，就两个核子的短程关联，相对于我在一个刀核里面形成两个核子的短程关联，它们之间的概率比是多少？就是说如果是它严格的是 NP dominant， 就是100%的 dominant， 它应该是6，对吧？因为一个12:2，所以它是有一个就大概是这个概率，但是它不是绝对100%，还有Fermi momentum，它跟 distribution 也不是严格的一对应，所以它稍微低于这个6的5点多左右，它大概告诉的就是一个概率，就是说我就大概有多少个质子和中子能成为一个对，这个概率。
好的，谢谢。
小鹏有个报告是吧？罗小鹏，有个问题是吧？
是的，马老师。李老师，感谢今天的报告。就是我们在 STAR 这个 Beam Scan 这个现在这个实验里面呢，我们现在正在测这个亲核产生，就是 Neutron、Triton， 然后 Helium-3 这些，也在测它们之间的 HBT 关联。就是我想我们的这个测量可不可以就是说来 probe 这个 spin isospin 的这个 interaction， 这个核子之间的。
我确实不知道，不知道这个从哪一个角度能够反映出来，就是如果那些 light particles 是 due to 这个 final state 的那个 coalescence 的话，应该能够就是 probe 在就是 freeze out 的时候做 correlation 的时候， 因为你比如说我看那个Neutron，它那个你最后那个 ratio 或者Neutron的 momentum distribution 应该反映就是那个就是它 contain neutron proton 的 momentum distribution。那个 momentum distribution 应该 carry information about 比如说 Southern correlation 或者 interaction in the earlier states, maybe in before freeze out. So maybe the momentum distribution of those light clusters can carry some information about 这个 symmetry energy 和这个就是 Southern correlation 这个。就是说没有做过，就是说不知道怎么 speculate 这个从哪一个角度上去讲这个问题，有可能我不清楚。
OK，
对，这个补充一点就是小鹏啊，补充一点，这个之前就是我们的这个分子动力学模型的计算，包括比如那个保安他们计算里面对这个党争关联，对这个质子的 HPT 的这个影响，我们具体的就是从束应模型的角度做过，那么发现呢，假如这个党争关联这个有高动量的尾巴的这个质子的话，它会导致 HPT 这个关联函数会压低，所以有这么一个这个现象在那里面，所以从这个角度来讲应该来说还是有效应还比较明显。
OK，
对，我也有个问题，就是关于小峰提的那个，就是我们在核物理这个反应里头做的 HPT 呢，主要是个长程关联，因为你是小相对动量的嘛，就是那个，但是这个长程关联呢，那个就是那个高动量刚才说的那个 SRC 呢是个 short-range correlation， 所以它应该是表现在大相对动量区域的这个关联函数的这个变化。所以这个从小相对动量的这个地方看，是不是能看到效应？刚才马老师说也有效应，我一直没有想太通这个事儿。我记得我是请谁也看了一下，我说把小相对动量的这个，就把那个 short range correlation 放到那个 transport model 里头去看看大动量，大的相对动量那个区域的关联函数有没有一些变化？那就是没做出来，反正。
OK，
因为这两个关联机制不一样，就是我们通常说的 HPT 是小相对动量。
对，你要看到那个。
但是它那个高动量的尾巴你这个质子之间的高动量尾巴，因为你去做这个做那个相对动量关联函数的时候嘛，因为它会对它的它扣这个分布会造成影响，所以呢，对它这个相当于这个小角度的动量关联函数也是会产生可观测的效应。
OK，
谢谢马老师，谢谢李老师。
我还有一个问题，那个李老师，就是说，刚才您介绍了一下将来的实验，就是比如说 GSI 它用 pick up 的 reaction 去测量那个高动量的那个 short range correlation。我在想，就是说这个，如果你让一个原子核激发起来，就是看它，比如说做一个特别风中子的系统，一个特别风质子的系统，会去看比如说 proton 或者 neutron 它的那个能谱，能不能在能谱的这个很高能端看到这两个系统的差异？如果这两个系统的差异如果有的话，能不能反映这个它可能来自 short range correlation 的高动量尾巴？
你说是把一个 nucleus 把它 excited to 它的。
对。因为激态的时候不好观测是吧？我就重离子反应里头，我给它激发起来，然后去测它的能谱。我就不知道，因为这个已经说这个能谱已经不是它最初始的那个动量分布了，所以这个能谱还能不能反映，就是它的高能尾巴还能不能反映这个 short range correlation？ 我不太明白。
这个你能谱是测的哪个？怎么测能谱啊？就是测什么 emission？
你比如说我现在做一个亚和124的反应，或者是听124的反应跟听112的反应，我就去看这两个系统里头的质子的能谱，就是在中间快速去看质子能谱，就想去看这个质子能谱在高能端有没有差异，这个差异会不会携带 SRC 的这个信息
？OK， 这个我 OK， 这个有可能。那个他那个走 Nightwish 他不是就是 一个月之前 post 了一个 paper 嘛，他们和就是 Jonathan 和那个 Chris Hago 他们按照他们已经有的 data， 就是 high band collision， 然后 look at 这个就相当于是我看是好像是 forward direction 的那个 particle spectrum， 就是 neutron proton 的 light particle 的 spectrum， 他们发现有一个 high momentum tail， 那个 high momentum 究竟是从 initial state 就 initial nuclear momentum distribution 还是通过 reaction 出来的，现在没有搞清楚。
OK，
就是有这种可能，但是就是那样，你像 MSU 他们不有一直做这个就是那个 spectroscopic 那个 factor， 他们从那里边提出这个sovereign correlation 这个 information。所以通过 study structure 就是这方面可以就是就是像 OK， 像他做这个 proton scattering， 他这个就是 measure 这个 particle spectrum， 然后做那个 dispersive optical model analysis 来 extract 的那个就是 target nucleus 里边的那个 proton occupation。那就是
什么？绿版的黄丹阳。
谢谢。
好，那接下来我们还有几个提问啊。那个白成明，白老师。
谢谢马老师，谢谢李老师的精彩报告。就是听了李老师的报告，我才知道张力力原来还有这么重要的作用。但是我们在做核结构研究的时候，有一个很麻烦的事情，就是张力力的差数不确定。就是想看看李老师从您的研究里边对张力力的差数有什么限制吗？
没有，所以就是OK， 比如说那个按照这个就是这个Maillard exchange 这个 theory， 这个 tensor force 主要是由这个在长程的是 due to pi exchange 对吧？短程的时候 due to 这个 rho exchange。rho exchange 的话，你可以把那个 rho exchange 的话，主要是 depends on 就是 rho Maillard 的 mass。所以像当年许昌做的时候呢，是用那个这个那个 Monkey Row 和 Jerry Brown 他那个 Maillard exchange model， 就是那个 due to 那个 tensor force due to rho exchange 来 modify 这个就是 rho Maillard mass in medium， 这样呢可以改变这个 tensor force 的 strength。你可以 introduce 一个这个 cut off 来这个 change 这个 range。所以的话，当时他讨论两个 parameter， 一个 southern range 的这个就是 southern range 的 cut off parameter， 再一个就是 strength of tensor force。play 这两个 parameter 呢，发现这个 symmetry energy 的 high density 的时候确实变化很大。所以就是在那个 Maillard exchange picture 里边呢，就是我们可以 play with 这个就是 rho Maillard 的这个 mass。我记得那个 Thomas Cole 和他的学生，还有那个Jeremy Holt 和那个Ralph 他们也讨论了，就是好像是 carbon 14的 decay time 还是什么东西会比较 sensitive to 就是这个就是 rho Maillard 的 mass， 就是 tensor force 的 strength。所以我也不太懂。你像人家就做这个就是 nuclear measure 算那个 saturation binding energy， 那个有这个 cost band， 那个结果非常 sensitive to 那个 tensor force strength， 都没有一个 constraints。所以现在就确实这是一个问题。我们比如说做这个 symmetry energy， 发现那个 high density symmetry energy 很 sensitive 这个 tensor force 的 strength， 但是呢没有 independent 的就是说 constraint 把这个东西能把它定下来，确实不知道。所以你这个问题我们也是同样的问题。
好，就是谢谢老师，就是你们研究的时候，这个张力力的强度是已经定下来的，还是就根据那个 rho 和派介质质量那些定下来的是吧？
对，那个现在是就是 model parameter 来 play with 不同的 roll mass 可以改变那个structural tensor force。那个里昂当时做的时候呢，就是你看他就是在 high， 就是在 large range 的时候呢，就用 AV18 里边的这个 tensor force， 这个 structural tensor force as a function of separation。在 large distance 的时候呢，0.8个 Fermi 之上呢，就用这个 AV18 里边的 interaction。在 low 的时候呢，因为大家都不知道，就是我们就用了几个不同的 model 里边用的这个 strength 来看对这个 high density symmetry energy 有什么影响。但具体你说哪一个东西，现在不知道，没有一个 probe 来能定这个东西。
哦，好的，
好的，
好，谢谢李老师。
好，接下来我们还有3个问题啊。第一个，请李洪娜老师提问。李洪娜。
李老师您好，我是那个北师大的刘洪娜。然后我听您的报告，那个我有一个问题，就是关于那个short range 的那个 NP pair。他们是在动量空间上是就是有一个 high momentum 的 tail， 那在空间分布上，它是在整个原子核里面是均匀分布的吗？还是也是分布在中心，还是表面？对这个您有什么 comment 吗？谢谢。
就是从理论上说的，应该是可以在就是在 nuclei 里边任何地方都可以，没有一个 preferred place， 就是你 high momentum tail 但是只是在 momentum space 有一个 tail， 但 coordinate space 那个 neutron proton pair 可以 anywhere。 这也是一个问题，就是说他们做实验的，比如说用那个 electron scattering， 大家都问，就是说你那个 final state interaction， 怎么能够就是说会不会影响你的 conclusion？ 尤其比如说用那个 proton scattering， 就是 knockout reaction， 最早在 Brookhaven 是用 proton scattering 来 study solenoid correlation。你跑出来一个 neutron 一个 proton， 那个 neutron proton 从什么地方跑出来的？是在 surface 还是在中间？如果是在中间的话，你中间过程那个 final state interaction 会不会影响你的结果？这都是很重要的问题。那个我知道那个欧汉在 MIT， 他和他一个学生，他们最近 analyze 一些就是去发展一个新的 code 来讨论 final state interaction。按照他们的 conclusion， 好像是也没有说是那个在 coordinate space 那个 neutron proton 究竟是在什么地方，是在 surface 还是 interior， 好像没有这个 information。
然后另外您说，比方说在那个风中子核里面，在那个就是 neutron skin 的地方 ，proton 会比 neutron 就是更快嘛，运动的会更快。那样的话，是不是在那个空间下应该形成 NP pair 的可能性应该会更低呀？你要形成 NP 对的话，他们必须得 momentum 要 match 是吧？通过这样理解，感觉好像它更趋近于在中心的地方，就是 neutron 和 proton density 接近的地方，可能是他们 momentum 运动的也一样快，然后更有可能形成这个 NP 对儿。
他们这个 NP 对是在 momentum space 里边就是 back to back， 相当于有很大的 relative momentum，total center momentum 还是 zero。就你这个
但是速度，但是速度应该相等是吧？方向相反，速度动量的大小应该相等。
对是。对。呀，这个很好的问题，我还要想一想，我不知道怎么回答你的问题。究竟就是那个 neutron proton pair 是在 surface 上形成，还是在什么其他地方？这个我不知道。
谢谢李老师。
用 correlation 就是测 correlation 或者什么那种办法能够说这个就是那个 back 那个 coordinate location 能把那个找出来，我不太清楚。
至少从实验实际观测这个 2N-SRC 的比值，不同原子核之间的比值。就是他发现它其实是有一个 saturation effect， 这个 saturation effect 就是说你原子核在增加的时候，它这个 NP 的这个 pair 这个 probability 其实没有增加的，不会随着你的原子核这个核子数而增加。所以这其中一种解释就是说你的 nucleon correlation 它必须是小于1个 femtometer， 但是你在一个非常大的原子核里面，比如说你5个 femtometer 的一个原子核里面，它很难让随机的2个原子核能小于，比如说你一头各一边，你想象它是个球形，它的两边的话，它形成了这个 NP pair 的这个概率是很低的。所以为什么原子核这个 A 在增加的时候，它的这个 2N-SRC 这个 A2 不一定是线性在增加的，它到很高的时候就 saturate，
但是
就增加的很慢了。
但是您说的这个 saturation， 它是相对于哪个参数？是相对于中子数、质子数，还是相对于指 NP 对的那个可能的组合数？
就是这个 A2 相对于，比如说你可以相对于这个nuclear number A， 也可以相对于这个nuclear density， 比如说 A 的1/3次方，这样的话你会发现它会有一个 saturation， 它不再增加了。就对，就像李老师看说这边有一个很多的综合，它已经挤在一起了，它没有线性的摊开，所以我们想理解就是说它可能是一个空间的效果，就是你很难让一个很大的原子核里面2个核子可以等同的概率去接近小于1个femtometer，如果它们离得很远，它们概率就是0。
那按照您的说法，还是可能中心的地方是吧？核子之间。
对，
相对距离小的地方可能更容易形成这样短程的 NP 对。
对，但是是说从我的理解来说，就是在研究这个原子核结构，我不知道坐标空间是不是一个合适的去理解这个原子核结构了。可能动量空间，就是在量子力学里面，可能动量空间会是一个更好的去理解它核结构的一个方式。坐标空间太难以想象，就是想象的比较困难。
好，谢谢您，
不客气。
好，下面请那个黄丹阳提问。黄老师。
李老师非常感谢您这个。李老师你好，这个非常感谢您这个报告啊，学到很多新东西。就是我们这个进程的关联这个事情很有意思。然后我们以前也要一直到现在，我们想要发展一个中高能的 PD 反应的程序。现在就是说有一点进展，但是还没做完，有个学生接着在做。这个我刚才听你的报告里边有一点意思，就是这个您说这个原子核里边核子分布的高动量成分，我看您好像提到过一部分是说，这个高动量成分来自于短程关联，这是我们一直都想要去研究的。您提到的还有一部分是说这个。有人说是 space 的一个作用，就是相空间的作用。我看您有个
OK， 就是
这个是怎么回事？
就是我是想解释那个就是那个 1/k to the fourth power 那个东西，按照那个谭斯纳清华的学生 famous graduate， 按照他的 argument。就是你那个写出那个就 two body 的那个 wave function， 就两个 particle at the coordinate R1 R2， 在那个就是 separation 变成0的时候呢，你那个 wave function 有个 asymptotic form 变成 1/r minus 1/a，OK， 然后你把它变到这个做傅里叶变换变到 momentum space 之后呢，你会出现一个 k minus k prime square，OK， 然后这个 momentum distribution。就你是这个那个 wave function square 就出现 1/k to the fourth power。按照这个东西的话，这个完全是就相当于是这个 1/k r encoding space， 这个 1/k momentum， 这个都是就相当于是 phase space 的这个 factor 一样。我说的那个就是那个是那个 Mossel 和那个 Lensk 他们 Gießen 那个 group， 就是相当于重复了那个。Birch 和戴尼的位置的一个工作，就是它是maybe 我有这个有这个 slide OK， 这是那个 Birch 和戴尼的位置，它的一个picture， 就是想讨论这个 high momentum tail 究竟是从哪里来的，它可以给出一个 analytical expression， 就是讨论比如说相当于是 two sequential two body scattering， 2个 nucleon 碰完一个 nucleon 变成一个 resonance，like direct resonance， 这个 direct resonance 又和另外一个 particle 碰，然后就是 final state 变成 K3 K4， 相当于是 two sequential scattering。这个 R 本身这个 resonance 相当于是一个 propagator， 它可以变成 offset， 然后他就讨论就是这个 offset 的这个 degree，OK。然后呢，从这儿呢，就是做这个 momentum distribution， 就像这个做这个integration， 然后把这个 就是 momentum distribution， how 就是能够算出来。这个 tail 的话，按照他们说，主要是就相当于是这里面出现一些 OK， 就这儿出现这个 rho square or k to the 4th power， 这个相当于是 analytically 从它的这个就是 phase space 做积分的时候出现这个东西。然后按照就是 Mossel 和 Lensk 他们那个study， 按照他们的 study 用那个 spectral function， 他说在他们那个 model 里边，这个 high momentum tail 就是几乎完全是由这个 phase space factor 出来的，而这个就是 off cell 的那个 dynamical contribution， 是比较小，这是我说的意思。那我不是特别完全理解你做的事情
啊，
就是
李老师，就是我谢谢你，这个对我来说是个新的信息。因为我们一直以为是说这个，以前了解的就是说这个 high momentum 这部分呢是由于相互作用引起的，但是如果这不是相互作用引起，只是因为相空间的原因的话呢，那这个意思可能理解就完全不一样了。
会 interaction 会有影响，要按照比如说你可以走为咱们讨论一下，就是说，当然这个你这个 momentum distribution 这个会 depend on the interaction use。可能这个就是这个 degree 不同的 shape 啊，就是这个 fraction、high momentum 各种东西会 depend on interaction。因为从那个理论上讲，假如你就有一个按照那个 Migdal 他这个文章里面他讨论，就用一个 second order perturbation 讨论给一个 interaction，OK， 做 second order perturbation， 你算那个 high momentum momentum distribution， 这个 fraction high momentum 这个是 proportional square of frame momentum times 就是这个 scattering length， 所以这个 high momentum 这个 distribution 会 depend on 这个 interaction， 但是这个 high momentum 会 1 over k to the 4th power 各种东西，就是相当于就是主要是由这个 phase space 决定。
我明白了，好，谢谢李老师。我还有一个问题，就是您提到这个有研究说质子在核的表面比中子跑得要快，这个怎么去理解？就是说，你如果从这个鞘模型的角度上去理解的话呢，你要说质子跑得快，你得说哪一个能级的质子跑得快，或者哪一个单粒子轨道上的。
OK， I agree， 我们呢现在是怎么说呢？就是说我们这个 picture 相当于是就是 based on 这个 Southern correlation study 做一个相当于是怎么说呢？我就是有点 naive 的一个 intuitive 的一个 model， 就是说相当于是这个 prediction， 我还没有看到实验上的这个证据，也没有看到，希望有人能够去somehow能 study。问题是你怎么测这个 momentum distribution inside the neutron skin， 这个我不知道怎么样。但是从理论上讲，就相当于是你这个就相当于 total phase space 的那个 density 是 conserved。如果在某一个区域的话，非常 Neutron-rich，OK，encoding space， 但 in momentum space 可能会反过来，这个 total phase space density 会 remains constant。somehow 那点就是我有这种 feeling， 但是没有 experimental 这个 proof。而且你说从那个 cell model 上考虑的话，可能你是对的，就是从 cell model 上怎么理解这个，我不知道。
我刚才觉得这个很有意思，我也一直在想怎么能够从实验上去，如果是这样的话，怎么去实验上去研究它。当然相对应的，我们设计什么样的反应去研究这样一个问题。好，我就这两个问题，李老师，谢谢您。
好，最后一个问题啊，我们留给刘卫平老师。刘卫平，
那个李老师，稍等一下啊，稍等一下。李老师能听见我说话吗？
我听见，我听。
对，就是报告是很精彩，就是在你一开始的，你有一个片子秀了一下，就是那个 symmetry energy 和那个密度的那个分布，然后呢，你就发现利用这个 neutron-star merger 呢，把那个很多 phenomenological model 都给 rule out 了，但是呢，似乎 就是 microscopic 和那个 ab initio 呢，符合的还不错。所以我有2个问题啊，一个问题就是为什么这个 neutron star merger 这个观测它有这么强的约束能力？第二个问题，如果说是按照这2张图的话，是不是意味着很多那个 phenomenological model 的路子，走的不大对？因为一般来说，从我们实验的角度来说，微象学的模型跟这个实验的符合更好，而这个微观呢，由于它比较基本，它符合的不太好。但这个似乎又反过来的，所以我想请教一下。
我们怎么说呢？就是说，比如你现在你看那个 literature， 大概有500种这个 phenomenological model， 大概300多种的这个 Skirm-Hardy-Fogg， 有200多种的这个 relative mean field model，OK， 各种 energy density function， 给你非常 diverse prediction。现在就是说，这个 neutron star 就现在就 canonical neutron star， 包括这个就是 massive neutron like 2.06， 我最后一个 talk 会讲到这个，主要 focus on neutron star 会讲这个仔细讲这个东西。就现在的 neutron star， 所有的 observation 都不能 fix the high density symmetry energy， 给你这个很大的 window， 不能 fix。虽然说现在已经有的这个 constraint from 这个就是 canonical neutron star， 或者是就是从 radii measure 或者gravitational wave， 能给这个 symmetry energy below 2 times nominal density， 特别是 around one， 就是这个 around saturation density， 就是你看那个 slow parameter saturation energy，around saturation energy 能够给一个就是比较好的 constraint， 就因为这不同的 analysis 这个20几种给的这个 symmetry slope of symmetry 差不多都是60左右，和以前我们知道都 consistent， 但是你要到这个 above 2 times nominal density， 现在 neutron star 的 observable 都不能 constrain 这个 high density symmetry energy， 所以我们是说，就是说建议说你要look at这个就是 neutrino 或者是 something directly from the core，OK， 才能 probe constrain 这个 symmetry energy 在这个 region， 或者是按照这个就是现在一些 calculation， 就是那个 after merger 那个 frequency 那个 spectrum of neutron star 会 sensitive to 这个 high density symmetry energy， 现在已经有一些 calculation， 但是现在的结果 neutron star 也不能把这个所有的 model 都 rule out， 给一个 constraint， 但是至少还有这些都 survive， 对吧？这边的话基本上没有任何 constraint。
好的，谢谢。
魏平，我不知道我没answer你。
对，我大概听明白了，